Hello and welcome to this presentation on the Unified Extensible Firmware Interface, or UEFI, on Oracle Linux. This provides an overview of UEFI. UEFI is a specification implemented in firmware, replacing BIOS firmware. The desire of UEFI was to overcome BIOS constraints, such as 16-bit processing and 2 terabyte drive size limit. Along with other improved features, UEFI provides greater security with the optional or additional feature of secure boot. Many UEFI systems can boot in legacy BIOS mode for backward compatibility via a Compatibility Support Module, or CSM. To boot in UEFI mode, Oracle Linux is installed on a system with UEFI firmware implemented. The system detects that it is in UEFI mode and uses the GUID partition table, or GPT, for the system drive. GPT is required for UEFI. With automatic partitioning, the installer will set up an EFI system partition, or ESP, on the /boot/EFI mount point, which will contain the files needed for UEFI booting. With manual partitioning, the ESP must be explicitly specified. Let's look at this boot partition. I'm logged into an Oracle Linux system. I'll run the df-h command to view the partitions. Notice that /boot/EFI is mounted on the /dev/SDA1 partition in this example. I'll run ls-l/boot/EFI/uppercase/EFI/Red Hat. This directory contains a first stage bootloader, shimx64.efi, the grub2 bootloader, grubx64.efi, and the grub2 configuration file, grub.cfg. This location for grub.cfg differs from its location in BIOS mode, where it resided in /boot/grub2. This describes the UEFI boot process. UEFI mode booting differs from BIOS mode booting only in its initial steps. UEFI does not use a master boot record like BIOS, but looks for and accesses an EFI system partition for files required for booting. The ESP resides on a device which uses a GUID partition table, which is required by UEFI. UEFI performs post and then loads a first stage bootloader from the ESP. The first stage bootloader then loads the grub2 bootloader. After grub2 is loaded, the boot process follows the same steps as for BIOS mode booting. grub2 loads a kernel image, then extracts the initramfs image. The kernel loads driver modules, then starts the systemd process. The /etc/default/grub file contains user settings for grub.cfg. I'll run the command ls-l/etc/default/grub. This file is in the same location as it is in BIOS mode. If you make changes in this /etc/default/grub file, the grub.cfg file needs to be rebuilt. To rebuild grub.cfg, use the grub2-make-config command specifying the output file using the -o option as /boot/EFI/uppercase/EFI/Red Hat/grub.cfg. We mentioned the globally unique identifier, or GUID partition table, abbreviated GPT. GPT is the type of partition table required by UEFI. In GPT, GUIDs are 128-bit numbers that identify partition types, provide unique IDs for every partition, and provide disk identifiers. GPT provides enhancements over master boot record, or MBR, such as larger drive sizes, more partitions, and data protection. The EFI Boot Manager utility allows administrators to view a boot menu and manipulate boot entries. For example, the boot order can be changed, boot entries can be created and removed, and the boot entry for the next boot can be specified. To view a summary of boot orders, run the EFI Boot Manager with no options. To view boot entries with more detail, include the -v option. Now let's have a look at this command. I'll clear the screen. If I run EFI Boot Manager without any options, the output shows there are 4 boot entries. Entry boot 003 is the boot current, which is the boot entry used to start the currently running system. The boot order is the boot order in the Boot Manager. The Boot Manager tries to boot the first active entry in the list. If unsuccessful, it tries the next entry, and so on. I can run the command again and include the -v option, and you'll see more detail. There is also a man page for this utility, so I'll run man EFI Boot Manager. You can see there are a number of options. I'll scroll down a few pages, and you can also see some examples of using this command. You can create a new boot option, change the boot order, change boot order for the next boot only, delete a boot option, and so forth. The last topic for discussion in this UEFI video is Secure Boot. Secure Boot is an additional or optional feature associated with UEFI intended to help avoid execution of malware during the boot process. Secure Boot steps are identical to UEFI booting without Secure Boot, with the important exception that it requires components to be signed and authenticated in order to be loaded and executed. Private and public key pairs are used for authentication. A chain of trust is established beginning with a first stage bootloader, shim, which is signed by Oracle and Microsoft. When shim is authenticated, the grub2 bootloader, signed by Oracle, is loaded after being authenticated by shim. grub2 then validates the kernel signature, signed by Oracle, allowing the kernel to be executed. All kernel modules included with the kernel RPM and those used with Oracle ksplice have Oracle signatures, and the signed/authenticated running kernel must validate them or they will not be loaded. This concludes this presentation. Thank you for watching.